So chemical energetics. Now remember, first thing, very basics. Remember, it's a small topic, not that detailed. It's you just have a couple of things in this, which you have to remember. Now, chemical energetics is first thing is you need to know what endothermic is. That's the first very basic thing. You need to know what endothermic is. Endothermic means energy is taken in. So it's a gain of energy. It's a gain of energy, and it has a positive value. The unit is usually kilojoules. So it's a positive value, and the unit is usually kilojoules. I mean, you can write it in joules as well. I mean, there's no problem in that, but they're mostly using kilojoules. The other thing is that you've got a reaction that is exothermic. Just one second. The other thing is you've got a reaction that's exothermic, which is going to be the opposite. It's going to be a release of energy. So it's a release of energy. Energy is produced. And that one is negative, and it's also going to be in kilojoules. So every reaction, you've got all sorts of reactions. You've got endothermic reactions, and you've got exothermic reactions. So I'll just give you some examples of endothermic reactions first. So plenty of reactions that are endothermic. An example is we can talk about decomposition reactions. I mean, most decompositions are endothermic. For example, you've got a carbonate decomposing. So that's like a calcium carbonate decomposes to produce calcium oxide. And it produces carbon dioxide. So that is an endothermic reaction. A nitrate decomposes and produces calcium nitrate, not calcium nitrate, it's going to produce calcium oxide and water and carbon dioxide, not water, NO2 and O2. And half of this and 2 of this. So that's another decomposition reaction. You could have another decomposition reaction that you should be aware of and that's a hydroxide. That is also, it can be decomposed to form calcium oxide plus a water molecule. So those are your decomposition reactions. Make sure you know of what is decomposition. Then you've got other reactions. You got changes of state which are endothermic. For example, you can have a substance. Endothermic would be going from solid to liquid to gas. So that's endothermic. What else is endothermic? You can have lots of other reactions. You can have photosynthesis, that's endothermic. So that's another example. So that's another example of an endothermic reaction. You could have what else? Photosynthesis. Remember what photosynthesis is. Sunlight is absorbed during this reaction. That is what photosynthesis is. And the reaction is that carbon dioxide and water molecules, they react. You need chlorophyll for this. And the two react to produce glucose and 6 oxygen molecules. So oxygen is also produced as a result. So that's an example of photosynthesis. What else is endothermic? You can have I mean, what else? Electrolysis is endothermic. So it's a chemical reaction where you need electrical energy. So electrolysis is endothermic. Energy is taken in the form of electrical energy. So energy is getting absorbed and it's getting absorbed in the form of electrical energy. Now, so that's one thing. And remember that whenever you have an endothermic reaction, there's one major thing that happens, and that is whenever you have an endothermic reaction, temperature decreases. So the temperature of the reaction drops. It's going to decrease. Basically, it is the temperature of the surrounding. You're always measuring the temperature of the surrounding, not of the substance. Like if I take in heat, I'm basically absorbing energy from the surrounding. So the surrounding temperature is going to drop. So the temperature decreases, and we always measure the temperature of the surrounding. We never measure the temperature of the substance itself. So the temperature is going to decrease. Let's talk about some exothermic reactions now. So which you should be aware of. The number one exothermic reaction. As exothermic, it's the opposite. Now, when you have an exothermic reaction, what happens is the temperature increases in an exothermic reaction. So the temperature increases in an exothermic reaction. And for an exothermic reaction, what needs to happen is that, I mean, what reactions are exothermic? First one, combustion. That is exothermic. Always heat is produced. So an example of combustion is most hydrocarbons, they burn, for example, methane gas in your heaters, in your cooking stoves, that's going to burn in oxygen. And it's going to react to produce carbon dioxide molecules and two water molecules, which is going to be liquid at room temperature. And this is going to be in gaseous state. So that's one example of an exothermic reaction. There are others as well. You got respiration. Respiration is kind of the opposite of photosynthesis. It's when glucose, your cells produce energy. They use glucose up. They react it with oxygen, and as a result, you get 6 carbon dioxide molecules, and you get 6 water molecules as well. So that's kind of the opposite of photosynthesis. What other reactions? A lot of nuclear reactions. Nuclear reactions, they produce energy in the form of radiation. They produce energy in the form of radiation. So what else is? I mean, plenty of other reactions which are exothermic, but for that you would have to calculate the energy. You have to do some working. So I'll just leave it at this point. Now, remember one thing. Is this clear? Quick question to the Mars, is this clear? Siddha, Hani, is this clear?
Yes.
Now the thing is that I'll just, whenever you talk about enthalpy change, I'll just give you a very brief idea first. Whenever you talk about enthalpy change, work is produced. Remember, a reaction produces work in two ways. When we talk about enthalpy change, one of the way a reaction produces work is, number one, it's the enthalpy change. Now, when you mention enthalpy change, you're basically talking about the heat that is produced, or vice versa, or vice versa taken in. Right? For example, if you burn a match, a heat is produced. I mean, you can see the heat. If you light a stove, there's a reaction and heat is produced. You burn wood, heat is produced. So a reaction produces work. That's the first way heat is produced. And then there's a second way a reaction produces work, and that is called delta S, which you're not going to study now, but I'm just going to give you an idea first. And that is the entropy change. I'm going to explain entropy change very briefly. You don't have to study this, but you must know the difference between the two. And no one is going to ask you about entropy change because that's in A2. But I'll just, in AS, all we're going to study about is the heat energy that's going to be produced. So we're going to study about this thing in AS, not this other thing. That's what you're going to study in your A2. Now, but I'll just give you an idea first, a brief hint of what entropy change is. Remember that you got a match, right? Let's say this is a match, and there's on top this is the thing that's burning. You light up a match and it starts producing heat, right? So it's an exothermic reaction. It's producing work done. It's producing heat. It's producing energy in the form of kilojoules. And you must have seen firecrackers that are kind of like, if you can see over here. So you must have seen these tiny firecrackers, right? And you burn that firecracker. So let's say this one is a firecracker and this one is actually, so there's a match that's burning and there's a firecracker next to it. Which one do you think produces more work? Like when you burn a firecracker, what happens? It explodes. And there's a lot of disorder created. Like it produces a lot of work. Like if it's a powerful firecracker, you're not going to put it in your hands because you know it's going to produce a lot of work and maybe damage your hands. With the match, you're not worried about that. Okay, so the idea that I'm trying to tell is that what is entropy change? Entropy change is that a system produces work in two ways. One is in the form of heat. You burn a match and you can see the flames coming out. That's heat being produced. And then there are systems where you don't see heat being produced. Like when you burn a firecracker, you don't see any flames, but you see a lot of disorder. So a firecracker, when it explodes, what it's going to do is it's going to create disorder. So it's going to create disorder. So there are two ways a system can produce work. One of it is by producing heat. The other one is by creating disorder. And that is how a lot of systems actually work, by creating disorder. For example, I'll just give you an idea of a steam engine, what happens in a steam engine. In a steam engine, you've got a piston and there is liquid water. There are liquid water molecules in the piston. And all of them are like really, really close to each other. When you heat it, the water boils and turns into steam. What does the steam do? The steam is kind of, they're very energetic and they are very disorderly. So what you do is a lot of disorder is created when water turns to steam. And because a lot of disorder is created, a lot of pressure is created and the steam piston starts moving up because the steam is going to push it. So remember, you don't see any heat being involved over there. What is involved is disorder. So just to give you an idea, brief idea first, because remember, this would be in A2, this would be part of A2, but you should know the difference. Every chemical reaction does two things. It produces work in two ways. One is by producing heat, like burning wood, it produces heat. The other one is like an explosive bomb or a firecracker. Instead of producing work, it produces a lot of disorder. And I gave you the example of a steam engine. How is a disorder created? You turn the liquid water molecules into steam. When you turn it into steam, the steam is very disorderly. The gas particles are haphazardly moving around and they start pushing the piston up. So that's how disorder creates work. So is the idea clear? Is the difference clear? Yes or no? Is this clear?
Yes, sir.
ठीक है, बाकियों को clear है? Raid, is this clear? Wafa, Oswa, is this clear?
Yes, sir.
Achha, but just a brief introduction to what entropy, like whenever you hear the term entropy, what does that mean? Remember, entropy is really important as well. So, I mean, so I'll just give you an idea. Like most people think that cars run on petrol in gasoline. Why? Because gasoline, when you burn it, it produces heat, which is actually wrong. We don't want the heat. Like if you burn gasoline, a lot of heat is produced. But what is your car radiator doing? It's constantly removing that heat. It doesn't need that heat. You don't want the car to heat up. So the thing is, the car actually works on entropy change. It doesn't really work on enthalpy change. Like, I mean, the same thing happens when you burn petrol. Like you take an octane molecule. So for example, you got a piston and let's say there are a bunch of this, let's say there's a single octane molecule. An octane molecule is, so that's your octane molecule, that's C8H18. Now, when you light it up, heat is produced, but we don't need that heat. Remember, a car engine does not work because it gets energy from the petrol in the form of heat. It doesn't want that heat. The car engine heats up, which is actually a bad thing. What happens is when you burn octane, you get lots of carbon dioxide and lots of water molecules. So a lot of disorder is created because all of a sudden one molecule turns into a lot of different molecules. All of a sudden, when you burn petrol, that's why the firecracker explodes. Because all of a sudden, this one molecule over here, it turns into lots and lots of carbon dioxide and water molecules. So it turns into, produces a lot of carbon dioxide and a lot of water molecules. So if you have a lot of disorder, the piston would start moving up. Is that point clear? I mean, is the idea clear? That your car engines, I mean, your car engine actually, your petrol, I mean, the heat that it's producing is kind of pointless. It's usually working on entropy change. But I just wanted to give you an idea of what entropy change was. Achha, is this idea clear? How the car engine works? Yes or no? Is this
Yes.
clear? Mahad, is this clear? Everyone else, Oswa? Okay. So we'll leave that aside now. But remember, there are two ways a system produces work. We're going to focus on enthalpy change in AS. We're going to focus on exothermic. We're going to focus on endothermic. A system produces work, a system takes in energy in the form of heat. So remember this, whenever you think of enthalpy change, you're basically talking about the heat that's being produced or the heat that's being taken in. Now moving on a little bit, and let's focus on enthalpy change now. Just ignore entropy change. Okay, we'll keep that for A2. Now let's focus on enthalpy change. Now the enthalpy changes, there are two things whenever a reaction happens. And we're going to do the first formula as well now. Whenever you see a reaction happening, for example, I've got CH4 and I'm burning it. So if I burn CH4, it reacts with two O2 molecules. The O2 molecules have double bonds. So there are two of them, both of them with double bonds. And they're going to react. And they're going to produce a carbon dioxide molecule. So carbon dioxide is, and they're only going to produce one carbon dioxide molecule, and they're going to produce two water molecules. So that's one. And that's the other one. So here's your reaction. Now, whenever a reaction happens, two things happen. The old bonds need to be broken. So you had these old bonds. They need to be broken. But to break them, you would have to give them a lot of energy. Why? Because you want them to be colliding with each other with a lot of force. So you want the molecules to sort of bump into each other with a lot of force, and you would have to make them energetic. Only then would the bonds be broken. So old bonds need to be broken, which is why that process is endothermic. So remember this, whenever bonds are broken, that part is endothermic. It requires energy to break bonds. You would have to sort of really, I mean, the molecules must collide with each other with enough force so that the old bonds get broken. And that force is, I mean, that energy that is needed initially, that's known as the activation energy. And then you've got new bonds. Once the bonds are broken, then the atoms can rearrange themselves and form new bonds. So new bonds are going to be they are going to be formed. And when new bonds are formed, that part is going to be exothermic. That is the part that's going to release energy. So every reaction consists of two parts. One part is that to break the old bonds, you would have to give it energy because the molecules need to have sufficient kinetic energy so that they can bump into each other with a lot of force so that the atoms can be dislodged. I mean, the hydrogen atom is at the moment bonded to the carbon atom. So you would have to kind of apply force to it so that, I mean, you have to make the collisions really violent, really energetic so that the bonds are broken. Endothermic, that's the first part, and then new bonds are formed once the old bonds are broken. And that part releases energy, and that part is exothermic. So is this part clear? Yes or no? Is this clear?
Yes.
Yes.
So let's we're gonna try and do the first formula probably now in the next class, TK, which is probably going to be on Wednesday. Tomorrow is a holiday, yeah. So we'll have it on Wednesday now, TK. Okay, everyone.
Okay. Okay. Allah Hafiz.
Take care, Allah Hafiz.